Welcome to HotChips 2024. Keynote 1, Predictable Scaling and Infrastructure.
I'd like to introduce our first keynote of this year's conference. It's my pleasure to have Trevor Cai from OpenAI come address us for the next hour. We've wanted at the program committee, wanted to go get the perspective of the big companies building big AI models and scaling to incredible large computer hardware. And Trevor is here today to address the scaling and also the infrastructure needs that drives. Trevor is currently at OpenAI. He's a member of technical staff. He's leading the OpenAI silicon and infrastructure efforts. He's actually firebred because he actually worked until recently on GPT-4, training GPT-4 on very large hardware systems. He's also been working on the GPT-4 vision models. Prior to OpenAI, Trevor actually worked at DeepMind, also on LLMs and LLM scaling. And Trevor, before DeepMind, was at USC, University of Southern California, where he graduated with a bachelor and then a master's. So this presentation will be about large language model scaling. Trevor is going to talk to us about how well these models scale and are predicted to continue to scale. You've all seen how large they're getting. So Trevor is going to tell us how much longer that scaling will continue. And he's also going to address what kind of infrastructure needs that drives. And then, of course, getting to these very large-scale systems, a bunch of new problems open up. And Trevor is going to tell us about the challenges they're facing right now, which is really straight insights for our engineering audience over here in terms of things we all need to become aware of and be supporting and help address. So with that, I'd like to introduce Trevor, and please give it up for Trevor.
Hey everyone, good to see you here today. Thanks for having me, and thanks to the organizers for making this such a seamless experience so far. As Ralph said, I'm primarily a research engineer by background, which makes speaking at HotChips a little odd for me. But I've spent the last year or so really thinking through and working on OpenAI's compute strategy, and in particular, working to help spin up our silicon and our infrastructure teams. Today, I thought I'd talk to you all about scaling laws and deep learning. After sort of doing an initial discussion of those, we'll talk about what these mean for infrastructure, first at a high level, and then some of the practical impacts that this might have on your work over the next few years. Let's start by looking back. GPT-4 and ChatGPT are both the result of a research agenda that OpenAI has spent more than 7 years and billions of dollars pursuing. We can call this agenda the GPT paradigm. You all have seen the what and the how of the GPT paradigm ad nauseum over the last year and a half since ChatGPT came out. In order to make ChatGPT, first we collected a large data set of text, code, images, audio, math, a whole bunch of other stuff. Then we pre-trained a model, which, given the previous words of a document, predicts the next word. After pre-training the model, we post-train it to encourage desirable behaviors and suppress undesirable ones. As a result of post-training, ChatGPT is able to follow instructions, it's able to be conversational, it uses tools, and it refuses to perform undesirable tasks. And I say it very simply, but of course doing all of these things is very involved. Pre-training the model requires scaling to a massive cluster of accelerators, and as a result, deploying many different forms of data and model parallelism. Moreover, even after we've gotten out of the pre-training phase, post-training requires collecting huge amounts of human feedback and doing reinforcement learning with human feedback, and really iterating on the results of the model to make them useful. Both of these topics could be the subject of a very long talk in and of themselves, but before diving into those, I thought I'd spend some time on the why. We've spent years and billions of dollars on learning to predict the next word better. But why does predicting the next word matter? And why should we spend so much compute on this? Back in 2017, before any of the GPTs existed, Alec Radford trained a neural network to predict the next character of product reviews. After doing this, he made a striking observation. One of the internal features of the network corresponded to the review sentiment. And harnessing the sentiment neuron resulted in state-of-the-art performance on sentiment classification tasks. You can see a visualization of the sentiment neuron up over here on this very short review. Green means the review up to that point is perceived to be positive, and red that it's negative. The review starts out pretty neutral, it starts looking good, and then it really takes a turn for the worse. Predicting the next character of these product reviews resulted in the emergent development of a high-level representation for sentiment. That's a bit of an incredible phenomenon, and it is not one to take for granted. Since 2017, we've settled on a high-level intuition for this phenomenon. Predicting the next word maximally well requires modeling the underlying process which generated the utterance. Consider a detective novel. At the end, when the detective says, "the culprit is," predicting the next word maximally well requires a memory of past events. It requires factual knowledge. It requires an understanding of human psychology, deductive reasoning, and much more. Or consider a mathematical proof. Predicting the next theorem or the next lemma maximally well requires understanding the flow of the logical argument being expressed. It requires understanding the degrees of freedom for moving forward in the argument, and which of these degrees of freedom will lead the argument a step closer to its conclusion. Moreover, it requires deep factual knowledge of what these degrees of freedom could possibly be from a mathematical perspective. Moreover, if the data that you're training on is the internet, the underlying generative process that generated the internet is the world. So by training these language models over subsets of the internet, what we're really trying to do is we're trying to understand the generative process, the world, that generated these utterances, these web pages, these blogs. This is an extremely grandiose intuition, and it's one that's worth pushing back on. However, it's also well supported by theory. Solomonov's theory of inductive inference suggests that a dataset of observations of a universe are best predicted by the smallest executable archive of that dataset. In other words, a short program which compresses the data very well. The negative log likelihood loss used to optimize these next word predictors directly optimizes for this compression. As a result, predicting the next word is like all great ideas in computer science. It's deceptively simple and actually quite deep. Since this realization, we've progressively improved our recipe for learning to predict the next word. We switched to transformers, we collected more and better data, we improved algorithms, and we massively increased the scale of compute. And at each step of scale along the way, new behaviors emerged. GPT-1 demonstrated that next word prediction enabled state-of-the-art language understanding. GPT-2, that a single model could generate coherent paragraphs of text and be applied to many tasks. GPT-3, that models could learn new tasks from just the context that they're given. And GPT-4, that a single model can do a variety of highly useful real-world tasks well. All of this comes just from predicting the next token. Here's one of my favorite demos of GPT-4 from when we tested it before releasing it. The model is given an exam for the École Polytechnique, the famous technical French university. The problem is in French, and it includes a diagram. But the model is asked in English to solve it. And it does. Doing this is pretty incredible, because it requires the model to understand both French and English, as well as the context in which it needs to use both, as well as the correspondences between the two languages. It requires the model to be able to interpret the diagram in the context of the text it's given, and it requires the model to have the understanding of what physical chain of argument would lead, most likely, to a correct solution. Scale clearly works. And yet, GPT-3 and GPT-4 were both high-risk models for OpenAI to have trained. How did we know it would work? And what gave us the conviction to train those models? In short, the answer is scaling laws. You can see one on the graph behind me. The x-axis is log compute spent on training the model, and the y-axis is the loss on our internal code base. There's not that many places where you can find a whole lot of code that hopefully isn't on the internet. And there's a curve which fits the shape of these points quite well. This is a log-log power law curve. This was first observed in 2020 by a paper called OpenAI, and I worked on a project later called Chinchilla, which fixed a minor bug in this original analysis. Both of these works observed that the final performance on the next word prediction task follows a log-log power law relationship between the compute spent on it and the ending loss. In other words, every time we double the compute spent on a model, the model's ability to predict the next word gets logarithmically closer to the irreducible entropy of the underlying generative process. This is the key miracle of deep learning. By simply training a bigger model on more data, you make an advance in AI. What's more, these scaling laws have predictive power. We trained a series of models that go from 10 billion to 10,000 times less compute than we spent on GPT-4. And then we drew the curve only using those models and observed that after GPT-4 finished training, it's almost precisely on the curve. The extrapolation here spans 4 orders of magnitude of compute. This predictable extrapolation is what allows us to have conviction to make big bets on this research program, to build massive clusters and invest increasingly large amounts of human resources into taming and understanding the clusters and the hardware, as well as the scientific basis of deep learning that we run on top of these clusters. That said, a reasonable response is, hey, it's not exactly clear how bits per word translates to how well models improve at real tasks that you and I might care about, like coding. Do those capabilities scale predictively? We took a look at this in the context of trying to make extrapolatory predictions about competition coding problems. Think LeetCode, code forces, that sort of thing. The result is this graph that you see. It looks almost identical to the one that I showed you previously. Here, the x-axis is still compute on a log basis. And now the y-axis is this thing that we call mean log pass rate. The mean log pass rate on a set of coding problems is computed as follows. First, for every coding problem, we take a huge number of independent attempts to solve the problem. And for each of these independent attempts, you grade them independently to be either a pass or a fail. You can then compute the pass rate for each problem. One problem might have a pass rate of 20%, another 80%, another 2%. Finally, if you take the mean of the logarithms of all of these pass rates, that is the MLPR, mean log pass rate score. Here, we're plotting the negative of that. We do this, and we use this metric instead of the average pass rate, because average pass rates are dominated by performance on easy problems. Mean log pass rate makes problems of all difficulties count similarly. That way, we're not just checking whether or not you can do a problem at 90% reliability instead of 50%. Using a scaling law defined before by models, again, 1,000 to 1,000,000 times smaller than GPT-4, we're able to fairly accurately predict the final performance of GPT-4, again, extrapolating this prediction out 3 orders of magnitude, 1,000 times usage of compute. But even then, log-log plots of that mean log pass rate don't really give you a human interpretable sense of progress. So here's a different way of viewing it. Here's a visualization of a different benchmark, the MMLU benchmark. In 2020, a group of PhD students at Berkeley made the MMLU benchmark, and they had hoped at the time that it would stand the test of time for evaluating AI systems. They really believed that this was the last benchmark that they would ever have to make. MMLU consists of a collection of different exams. Think the types of things that high school and university students would take. 2 years later, GPT-4 scored just shy of 90%. What log-log scaling obscures is that slow progress turns extremely fast on human interpretable scales. And now, with the benchmark almost entirely saturated in 2 years, we've identified many of the questions that we're getting wrong are actually scored incorrectly. The quest has begun to find new benchmarks to track the progress of these systems. So let's recap. So far, we've taken a trip down memory lane and established that next word prediction is a meaningful thing to optimize, that there are immense returns to scale, and that these returns are predictable and extrapolative, both for the underlying loss function as well as the capabilities that the model can demonstrate. What does this mean? Well, the first and the most obvious implication of scaling laws is that they reward ever larger frontier training runs. You can see this in the empirical data. This is a graph of flops used by frontier AI training runs since AlexNet started the deep learning Cambrian explosion in 2012. Epoch AI reports a growth rate of about 6.7x a year until 2018, and a little more than 4x a year since then. And even though Moore's law has, of course, been a tailwind through this period, this astonishing rate of growth far exceeds that. And it's driven primarily by two things. One is, of course, innovations in precision and chip architecture. But the other is massive increases in the scale and the wall clock time consumed by frontier training runs. We see the same thing internally. GPT-1 was trained on a single box of GPUs for just a couple weeks. GPT-3 was trained on a cluster of 10,000 V100s. And in the words of our partner, Kevin Scott, the CTO of Microsoft, GPT-Next will take a whale of a cluster. As long as we see these scaling laws continue, we will move heaven and earth to try to continue our progress down them. That isn't to say that there aren't immense headwinds to continuing down the scaling laws. Again, let's revisit the kink in this curve in 2018. What happened there? Why did the rate of progress slow down from 6.7x a year to 4? Well, Epoch's best guess is that low-hanging fruit like hardware matmul units and operator fusion were picked. So we entered a regime in which progress became meaningfully more extensive to maintain. There was an overhang of sorts. On the algorithm side, moving forward, we're going to have to grapple with some hard problems, like data availability. And as we talk about the next couple order of magnitude increases from current cluster sizes, we'll enter a regime in which dollar and energy costs of these clusters will become significant, even for some of the most free cash flow generating companies of history. Physical limitations on how long it takes to build energy, interconnect it with our already growing US grid, and construct massive projects in single geographies will become more and more relevant. So far, we've only talked about training models, not serving them. For me, it's actually much harder to speak specifically about inference than training. It's a little harder to forecast, and moreover, we can plan training infrastructure ahead of time. But inference capacity builds are somewhat guided by market demand of the products that you're inferencing. However, I think there's a few statements that I can say that have guided our thinking thus far. The first is that the vast majority of OpenAI inference GPU hours are spent serving our most advanced models, the GPT-4 variants. GPT-4o Mini, GPT 3.5 Turbo, other such models, at the end of the day are really a drop in the bucket compared to the compute that we spend on the GPT-4s. I expect this to continue into the future. The second thing we observed is that the ratio of GPUs purchased for inference versus training has climbed enormously generation over generation as the models have become more intelligent. API demand for GPT-2 would have been approximately nothing. GPT-3 had a fairly small API demand, certainly much smaller than the size of the training cluster we trained it on. And the continuous demand for GPT-4, 24/7, 365, since we launched it, has been significantly higher than the GPT-4 cluster size. This is another trend that, again, I expect to continue occurring. Finally, in the last 12 months, we've dropped our pricing on GPT-4 by between 12 and 24x. And what we've seen is by doing these price drops, we have moved dramatically to the right on the price quantity curve. The cost per unit intelligence has dropped significantly, and I expect it to continue dropping into the future. All in all, this leads us to a very quick 3-point bull case for the need for large quantities of AI compute. First, predictable and extrapolative compute scaling enables high conviction investment in training infrastructure. Second, intelligence drives inference demand. And third, the technology and the economics for scale are ripe to be picked this decade. All of this leads me, and OpenAI more broadly, to the following belief. The world, not just OpenAI, but the whole industry, needs dramatically more AI infrastructure than the supply chain is planning for. This was true in February. I believe it's still true today. I'm all too aware that the arguments that I've made thus far in this talk roughly correspond to the following. Believe in straight lines on a graph. And indeed, most straight lines on graphs with logarithmic y-axes eventually straighten out. But often, lines really do just keep going up for way longer than anybody expects. Here's a graph of the historical trend on solar generation capacity over time. The real data is in black, and expert predictions at each individual year are overlaid in color. What you can see is that over and over and over and over and over and over again, the WEO refused to look at a straight line going up on a log-log plot. And they were wrong repeatedly as a result. Here's another line that went up. You're very familiar with it. It's Moore's law. It may have flattened out eventually, but for 50 years, far longer than anybody in the 70s would have thought reasonable, this line just went straight up. On a recommendation from a friend, I recently read some obituaries of Bob Taylor, who founded and led Xerox PARC's computer science laboratory, where the modern personal computer and the GUI were invented. It struck me how crisply he saw the future of microcomputer proliferation, of the rise of mobile devices, and managed to predict these within an error bar of only a couple years. He lived in the future by looking soberly at this line. Just like Moore's law, keeping the log-log line of compute versus loss straight is going to require monumentally increasing investment on both a human and a technological level. It could flatten out eventually. But that straight line has held over 8 orders of magnitude. And straight lines on graphs that hold for 8 orders of magnitude are hard to find. I would be really sad if I threw away my time machine. So what does that mean practically for you? In short, design for the realities and the constraints of mass deployment, in particular, of data center chips. I'll dive into 2 examples: reliability, availability, and serviceability, and power management. The next generation of at-scale clusters will pose massive challenges to RAS. Just looking at optics alone, with sufficient scale, the mean time between failure can be measured in minutes. And that's without even including much more common sources of failure: ECC errors in GPU HBM, board failures, VRs, PCIe connections becoming unseated, and many more things. Not only are hard failures becoming more common, so are soft failures. Silent data corruptions occur disturbingly often, and even when we're able to isolate the GPU that is known to have performed it, sometimes it's unreproducible. Finally, as many of you have heard repeatedly, these failures have an extremely wide blast radius. If we continue doing synchronous stochastic gradient descent over these clusters, one GPU failure could mean the pause of tens of billions or hundreds of billions of dollars of equipment. Addressing these challenges is going to require a collaboration between both the hardware and the software. We have to change the paradigm in which we train, but the hardware needs to present and give the hooks that are needed in order to maintain high availability. Here are a few specific things for you to consider when you're making RAS choices for your own hardware. First, minimize the cost of repair. Previously, we lived in a world in which if something went wrong, we could just hard crash the process, have everything spin down, get back to a happy state and spin it up. And this works even for tens of thousands of accelerators. This eventually stops working. Before, it wasn't a huge deal if every single failure caused a process crash. Now it is. For failures both common and uncommon, I urge you to consider how much and how to make each and every one of them as low cost to repair as possible. We would prefer a CPU exception that we can catch over something that requires a process restart. But we'd prefer the process restart over something that requires doing a firmware reset. But that even more than a node reboot, and that over an RMA. As an example, ideally, failed writes over scale-up networks should result in catchable exceptions on the host doing the write. So that way we can reroute and figure out how to make choices moving forward. Another thing to think about, minimizing the blast radius of failures. As an example, one thing that we observe in real life on real clusters is that link flaps on one port can sometimes affect the neighboring ports and cause those ports to flap as well. Ideally, this shouldn't happen. We want, if one thing fails, for everything else to not have to fail. As another example, ideally uncorrectable memory errors should only affect the GPU on which they occurred. In practice today, in the presence of a coherent memory fabric, this is a hard guarantee to provide, but it's an important one. Even more than that, once you've thought about how to minimize the blast radius and minimize the time to repair, consider graceful degradation. Not all failures have the same priority for technician time. An accelerator that's completely off the board and not responsive is much more worth a technician's time than losing a bank of secondary memory. We would like to be able to live in a world in which we're degrading hardware appropriately until a technician has the time or is already in place and looking at the relevant host to service it. Finally, combined with all of these things, as much validation as possible needs to be able to be performed in field in an automated manner in a fast and extensive way. I'm aware that's a lot of things that are sometimes in conflict. However, using the SDCs as an example, it's crucial that we be able to perform in-depth correctness checks of the underlying hardware once we've managed to accuse a specific accelerator of having performed an SDC. Moving on to power. The constraints of deploying this many accelerators at a massive scale are going to mean that we're going to run into power constraints eventually. We need to be able to make the most of the power that we do have. Synchronized training of massive clusters also results in a fun phenomenon. Just like an orchestra going from soft to loud, soft again. GPUs in a synchronized training job draw power in the same way. And this has suboptimal implications for both the grid that's providing the power to the data center, as well as for the equipment on site. We have physically heard buzzing transformers. As a result of both of these needs, we need to be able to, at both the cluster and the individual accelerator level, get low latency power telemetry. We also need to be able to provide out-of-band power management in order to manage both of these things, just to make sure that we're being a good citizen on the grids that we're running on. Taking that a step further, to make the most of the power that we're giving, ideally we want to be able to slosh the power across different accelerators that have different needs. Again, this requires out-of-band management and controls at the accelerator and at the firmware level and the driver level to see what we're doing and place the controls that we need to make the most of the power that we have. I could keep going and talking more and more about what this means for security, what this means for scale-up networks, what this means for everything else. But instead of overloading you with too many things in the concrete and the specific, I'd like you to just keep these 4 takeaways as you walk away from this talk. The first is that predictable scaling is the underlying engine that allows companies like OpenAI to make deep investments in AI training compute usage. The second is that delivering AI to the world will demand massive infrastructure build-out. The third is that as a result of both of these implications, we need to collectively design for mass deployment of any hardware that we build. And finally, performance is only one of these requirements. Power, security, network, and reliability are all crucial ingredients here for us to work together on. Thank you for your time and attention. We have a lot of work and, frankly, difficult technologies ahead of us, and I'm excited to tackle them together with you all. Thank you.
Thank you, Trevor. That was a fascinating talk. We will have a lot of time for questions. Maybe I'll take the chance to ask my own questions first. So fascinating story about scaling of language models. And of course, with every step you said, new experiences get enabled. Could you imagine, if you look ahead a little bit, as the models get larger, what new experiences we might see coming down the road?
You know, that's a really hard question because we asked the same thing before GPT-4 came out. And it turned out we weren't very good at making these guesses. So I'm a little afraid of, guessing out to GPT-5. But for me, a couple things that I think are going to be big are, one, I expect reliability of these tasks to improve massively. We saw this already with going from GPT-3 to GPT-4. Sometimes GPT-3 had flashes of brilliance, but not consistently. A second thing I'd expect is much better reasoning over long horizon tasks. Right now, we see many models sort of starting to fall apart as they progress into multi-step steps. And I hope that these get better.
That's really good. How about a related question? Energy efficiency is still pretty low, at least compared to what a human brain can actually deliver in terms of compute per energy. Any guess as to what experience we might enable if we had, I don't know, 2 or 3 or 4 orders of magnitude lower or more efficient compute available, an AI brain in your pocket?
Yeah, the first and the most obvious thing is I would plow all of that back into training an even bigger model if I could. Past that, there's, I think, quite a lot of things where deployment outside of data centers are constrained. Sometimes by memory, but also sometimes by memory efficiency. Power efficiency. And I'd be really excited to see truly live on phone, for example, speech-to-speech, in the same way that we've been able to demo successfully with GPT-4o in the data center. I think that'd be very exciting.
Yeah, that's really great. And then I have a question on your take on AGI, but we'll take that some other time. Alisa, do you want to turn it over to you for questions from online?
Got it, thanks. And thank you for your talk, Trevor. So there's been some questions out there. We spend a vast amount of money on training these models. Some of the questions that are coming up is, do you have any real data on the ROI and the enterprise use cases of these models? Like, training's one thing.
I take a lot of comfort in seeing how many people are using models like ChatGPT and Claude, and real consumers who have real financial constraints paying OpenAI money out of their pockets to use the models. I think that it indicates quite a lot about what the underlying value these models are providing them.
Okay, thank you.
Why don't you ask another question from online?
I'll just keep going. So this one's from Mario Shalabi. He's talking about your log-log scaling and wonders if that isn't just a function of how you scale the network. Is there some assumption that the network is based on attention layers and that's what's driving the way your graph is shaped? Yeah.
In the 2020 paper that first started the scaling laws for neural language models trend by Kaplan et al. In 2020, they also performed this analysis on LSTMs. Those don't have any attention layers. You see the same type and functional fit of log-log scaling between compute and final loss. The difference between LSTMs and transformers is that transformers have a curve that lies lower. More broadly, there's been a lot of work in the machine learning community to characterize scaling laws outside of the realm of neural language modeling. There's been work on, of course, language modeling of code, but also on modeling multimodalities, and even on games, game playing with reinforcement learning. You see the same sorts of log-log scaling laws emerge in many domains. These are empirical observations. As of yet, I'm not aware of a particularly strong theoretical grounding for these things. We see the same pattern pop up over and over and over again, and I personally suspect that is indicative of a deeper truth that we don't know yet.
Okay, thank you.
We'll go for a question in the room over here on the right.
Hi, Tanj Bennett, Semi-Analysis. This is actually a related question. If you were to take competing models like a mixture of experts and so on, and as you just indicated, the log-log laws are the norm, are they parallel? Or is there an indication that they're converging to something? Do all of them seem to learn by scale at roughly the same rate? So if you transfer to a more promising model, are you on a fundamentally better track?
Most of the public work in scaling models has generally shown parallel improvements. However, one thing, for example, that I'll note is in 2021, I worked on a paper scaling laws for a mixture of experts. And there, we did see a different slope between different scaling laws. So I think you can see both parallel lines as well as lines with different slopes.
Thank you.
Please go ahead.
Hi, thanks for the great talk.
If you state your name and affiliation.
Yeah, my name is Padmaja from Apple. Considering scalability, I think security is a contradicting word here, but want to know the efforts that are being put for the security and also the correctness of the data where it goes to some very critical areas like health and so on. So any comments on that?
Yeah, definitely. First, to be very honest, I'm not a security expert. That said, we have quite a dedicated security team, and I think a lot of the efforts are traditionally around some straightforward things of protecting model weights, protecting consumer data, making sure that the inputs for one consumer don't affect the outputs of another, so that there's crossing of streams. That said, we've published some blog posts about the directions that we're excited about in the future. One of these things, for example, is confidential compute. It's not something that we've been able to deploy in production as of yet, but we think it's going to be an exciting direction for us in the future.
Okay, about the correctness of the data for critical areas?
I'm not quite sure what you're asking. Can you clarify?
Like any health-related stuff, when you go and try to explore on your platform, you need the accurate data, not something which has 50% accuracy. So how do you really stress on those kind of scenarios for those particular critical fields where many people will be relying on?
Are you asking about verifying the correctness of outputs?
Yeah, verifying the correctness. That's good. Yeah.
I don't have a great answer for you. I would defer you to our policy team. Okay. I imagine what they would say is human in the loop is going to be critical for the near future.
Okay, thank you.
We'll take another question from this side.
Hi, I'm Ifil Shahian, Rain AI. Thank you for the fantastic talk. I was wondering when it comes to power consumption, if you can comment on how much of the power is going into the compute versus data movement in memory versus networking, and what is the arithmetic intensity that you see over all these workloads?
Yeah, so for training models, typically the arithmetic intensity is not too bad. We try very hard to make sure that we're able to stay in the flop span regime wherever we can. As far as the energy used in moving data around as compared to doing computation, I think what we see is not going to differ significantly from what you will see when you do micro-benchmarking of other models in the open source world.
How about inference workloads?
Inference workloads definitely have lower arithmetic intensity and spend a lot more power on doing weights movement, in particular for applications with sensitive latency constraints on the token output rate.
Go ahead.
Hello, this is Dmitry from WRC. I have a question. So you mentioned so I was just curious what you do when you have a GPU failing, right? Whether you just use standbys to replace the failed GPU, whether you drop the whole data parallelism group, what do you guys do? Then I was wondering if you could also talk a bit, how do you implement that actually in terms of the tools and then the hardware, all that stuff? I'd really appreciate that, thanks.
Yeah, the second question is easier to answer than the first. For the second question, we just have a whole lot of C++, Rust, Python, control logic going on. For the first, we've investigated techniques like both hot spares, dropping things, so on and so forth. The situation in which you would use each of these is frankly just going to be different depending on the scale of the cluster, the mean time to failure and repair for that cluster, and the model that you're training.
Thanks. I was wondering if you could just summarize what you guys are doing right now. So it seems to be that you guys are not implementing fully. So whenever you have a failure, GPU failing, then you just roll back to the last checkpoint and then just restart the whole thing. Is that correct?
It's hard for me to talk about what we do for our frontier training runs.
Lisa, why don't you go back? Let's go back to you.
Certainly. Do you think that the current GPU paradigm, writing Moore's law and the new algorithms that are invented, think that's going to be enough to get 10x better performance on tasks? Or do we need a completely new paradigm?
It's a technology question, but perhaps we'll turn that into, like, say, a processor architecture question, right? We have a bunch of CPU and GPU architects in the room. Do we need a completely different processor architecture, or are we doing fine with what we have today?
That's honestly something that I would defer to you all on. I train the models.
You have a room of experts over here to help you with that question.
Perfect.
We'll take one more, Lisa.
Okay, let me grab another one here. Sorry. This one was an interesting question. It's a bit of the mirror in the mirror. Knowing that GPT gets trained on data from the internet, what's the risk or impact if the LLM starts being trained on data that's generated by itself?
Oh, it's actually quite fascinating. This is something that I think we've been doing quite a lot of study on recently. There's been quite a bit of external work talking about how models eventually collapse if they're repeatedly trained on corpuses of 100% their own data. I'm optimistic that we'll find ways to make these things useful.
Okay.
Please go ahead.
Vijay from Harvard. So you talked about two of the fundamental pillars of machine learning, right? You spoke about models, you talked about infrastructure, and the third one is data, which you talk very little about. And this is alluding to the point around the MMLU benchmark and so forth. So I'm kind of curious, could you talk about scaling laws around data and what data could actually do in terms of being a system optimization knob?
Yeah, absolutely. So when I talked about the scaling laws, I'd mentioned the original analysis in 2020 and the small bug that we had found in 21-22 on Chinchilla. That specifically was, instead of looking at scaling laws, which are power law between compute and final loss, whether we could break that compute term into parameters used in the model and the data that you train it on, assuming that you're only taking one pass through an infinite amount of, arbitrarily large amount of data. And what you see is, instead of scaling mostly the parameters in your model, you want to scale roughly evenly the data that you pour in, as well as the parameters in it. So data quantity is, in the current methodology of training transformers, going to be very important.
Thank you. Jeff, go ahead.
Jeff Smith, thanks for the great talk. So maybe you can't speak to the exact CPU or GPU architecture changes that you envision to facilitate new models, but can you speak to the degree relative of improvement that you guys are requiring in your growth models to keep this thing going? Like how much more are you guys expecting the next 5 years in terms of, flops per watt or supply chain growth or model design? What's to be fueling this improvement in the future, given we can't, clone, TSMC and Samsung tomorrow, or put 10% of like the, gross global product in semiconductors overnight? How are we going to keep growing?
Yeah, absolutely. I think in many ways the answer is the inverse, which is we'll look at all of the constraints that we're operating under, find the first one, and then say, hey, this is the cap of what we're able to do at this point in time if we're not able to break through that first constraint. And then, of course, the problem-solving methodology then is to go break down the constraints one by one. This is, as I mentioned briefly, like quite similar, I think, from the outset at least, how it seemed like the foundries attacked Moore's law. It requires more and more and more effort on our part to continue marching down this curve of how much compute we spend. And if the first bottleneck here are the logic foundries, or if the first bottleneck here are the memory foundries, or if the first bottleneck here is power, or the amount of capital that we have available, like we'll just go look at which one of those comes in first. And
are you able to share right now, like whose doors you're knocking on to fix the most urgent problems, and kind of share what those first choke points are going to be?
Yeah, I think at the moment, at least OpenAI has been engaged with all of the industries I've mentioned pretty broadly. It's very clear that the obvious limits are going to be hit quickly, but it's not clear once you break open that first bottleneck where the real bottlenecks are going to lie afterwards.
Thank you.
Please go ahead.
Thanks for the great talk. Generally, FutureWay. Allow me to ask this question from like a capital investment and allocation viewpoint. Earlier this year, we heard of the total investment should be $1 trillion, single digit, by the way. And then 300 billion, and then maybe 100 billion in the next 6 years so far. I guess my question is two parts. One is, I assume you're going to invest more in the inference. So between training and the inference, like, because you are in charge of the infrastructure, how much you want to, percentage-wise, to invest into each part of this. And then within the inference, my understanding is, if I were you, I would develop my own inference processors. So are you going to do that? Or you think training, you should cover training by in-house GPUs or accelerators too?
Okay, so first I'll say that Trevor does not have a master's in economics. So I'm not sure you want to answer that question.
I checked that, but...
feel free to only respond to what you think you can answer.
I think, as I said in the talk, the key thing on inference is it's going to be demand-driven, right? So we're just going to have to see demand in order to know how much inference we're going to be deploying. That said, as I said in the talk, there are a couple things that we believe are going to drive a whole lot of inference demand. The first is that we see repeatedly more intelligent models require the largest number of GPU hours by far among our current fleet. And the second is that we see, as we step up this curve, the ratio between what we spent on training and what we spend on inference continues to grow, right? So we'll have to see how the market reacts to the new products that all of the companies build, but I expect the amount of inference capacity to continue growing.
Okay, great, but for the total amount, there like a ballpark number?
No.
No. Thank you.
He's not a financial expert. That's not his job. We'll go back to Alisa.
Yeah, this one came from David Weaver at Akina Inc. So actually, not the one I was going to ask, sorry. Different question. Today we had IBM talking about the demands for system uptime for their mainframes. If you had to make the trade-off and say, I might have slightly lower performance systems, but I'd like them to be up more consistently, how much performance, perfect performance, would you be willing to give up to just have them stay up? 99.999.
Yeah, I think the right way to look at this is just look at good put over time. And you can maybe approximate that by taking performance times the expected uptime under a set of software regimes and assumptions on time to failure and time to recovery, and make your judgment on whether you'd be willing to sacrifice performance for reliability or vice versa, depending on how that product moves.
Okay, so this question was to you because we expected you to kind of maybe have a sense of that.
I think in general, most of the things that I talked about in that talk do not require massive sacrifices in performance, and I think it would be very hard to stomach, for example, a 5x drop in performance as compared to trying to figure out how we can make the system as a whole through software run faster.
Okay. Thank you.
Let's go ahead.
Hi, this is Amit from AMD. I have a question related to SDCs. It's a two-part question. Does OpenAI have metrics on how many times unreliable results occur due to SDCs? And second part is, what is OpenAI doing to mitigate or root cause these issues, especially at the hardware level?
I don't have the metrics off the top of my head. Of course, detecting SDCs is a
it's tricky.
sticky subject given that they're silent. What was the second part of the question?
What do you usually do to basically mitigate or root cause it? Because it's a very tricky issue. So especially the hardware level, because from the background.
Yeah, we have a suite of diagnostics that we use to test an accused GPU and some fun tricks to, when we detect abnormalities in the computation, make some wild guesses of who to accuse.
Please go ahead.
This is Tian from Frontier Research. So you mentioned the performance is predictable from scaling. Does that mean the timeline of AGI is also predictable?
No, I don't think so. And I think part of that is because the definition of AGI is ever moving. There's some famous quote, right? Like AI is whatever computers can't do yet. Yeah, I think you'll note that I intentionally avoided saying AGI as far as concrete timelines. I expect progress to continue and for us to continue running down these curves. As far as how you want to classify the systems is a different matter.
Thank you.
Okay, now I'll come to David's question. So you mentioned that post-training is used to train the model to avoid undesirable behaviors. How is it determined what behavior is undesirable? Is there some sort of bias that may be introduced in who makes these decisions? What's the process?
Yeah, this is something that our policy team can speak to much more crisply than I can. In general, there are things that are illegal to do, and the societies that we live in generally consider bad behavior. Think things like CSAM. And we try very hard to make sure that our models do not participate in those activities.
Okay, so some of that might be driven by direct regulation and other is driven by an ethics decision that's made somewhere. That's kind of what it sounds like.
Yeah.
Thank you.
The way that Sam has previously talked about it publicly, Sam, our CEO, is that within broad bounds, we would like to find a way to get users to be able to specify their preferences. And within a narrow bound of things that society has deemed improper, not do those things.
Thank you.
Please go ahead.
Sorry, allow me, Jen Lee, Future again. I'm going to follow up another question asked earlier from a different angle. For training and for reference clusters you have right now, what's the current utilization rate for the compute? I mean, this is for the system architects in the audience. I guess this is a fair question to ask.
It's a hard question to answer, and especially in the new world of thermally limited performance compared to the theoretical spec of boost clock rate times flops per clock, it matters a lot what you put your denominator as.
And as you put earlier, I guess the utilization rate for inference is lower?
In general, I would expect commonly that to be the case.
Thank you.
So thank you, Trevor, for coming by. Thank you for sharing these insights with us. Thank you for answering all our questions.
Thank you all.